Okay, so yeah, today I'm going to talk a little bit about vehicle dynamics, testing, and why we care. So here's a little bit of background. And I think, so here's what I kind of realized is that like, I had in my head all of these concepts that are like, oh, I know these are really important to like making a car go fast. And obviously like, these are what people need to know, and we're going to be testing the car, and it's all going to be like really great. And like the suspension team is going to be awesome next year and like make the best suspension the world's ever seen. And I sort of like had all this like process and stuff in my mind, and I realized that like none of that has been communicated, or like none of you all are probably on the same page, just because you know you're new to the team, and I've sort of like been here for a while, seeing some of these changes and stuff made. So I just wanted to give a little background and context about sort of like where in OEM's history the suspension team is right now. So 2 years ago was when I took over as a suspension lead, and it was me, John Zarez, and Owner, as well as Naomi was working with us and Neil was working with us. And this was kind of like the summer of 2018, and we got like really roasted at the Formula North competition that summer. So at the start of that summer, we got a competition, absolutely flamed. I'm sure I've told the story before, but like, you know, there's like a little note that said like we hardly understood like 25% of vehicle dynamics. And we were like, damn, this is brutal. We want to do better. So our team over the summer spent a lot of time. We just kind of like started from scratch, like started reading RCVD, started like just doing as much research as we could. And we did like a lot of good work. Like we took the team from like basically just designing a complete arbitrary suspension, not arbitrary, but like not a very like well thought out suspension system. And took that to like, we are considering things, we are trying to make intentional choices about the design. And we kind of like made progress in three main ways. One is we made a lot of progress using tire data. So we actually bought a subscription to the Tire Testing Consortium. We bought a new tire data analysis software called MF Tire, which we have access to. And we sort of started out by making a new decision about what tires we should use, and ended up switching to a smaller set of tires, and sort of had some data to back up why we thought those tires were the best. And then sort of from there, we moved on to actually like some basic MATLAB models of some stuff, which we made like some pretty useful models, not exhaustive, and there's like so much more we could do, which I know we've talked about in other meetings, but we sort of like made a lot of progress in that, generating a lot of useful scripts that I will explain what they do and how they work in like the next couple of weeks, because they're really essential to designing the suspension system. But we made a lot of progress sort of making some of those tools. And then finally like made a geometry that accounted for a decent number of effects, like was fairly well thought out, but was certainly far from perfect. And like in all this analysis and all this like design, I mean, I don't think we like use the words oversteer or understeer once. Like that was just not part of our vocabulary. That was not part of our understanding of vehicle dynamics. Like we were just trying to get a baseline. Like we have tires, we have springs, we have a suspension A-arm system that needs to like move up and down. Like we didn't get that much further than that. And there's like worlds, there's universes more to dig into. And so the thing that's really holding us back the most as a team is, and I'm sure you guys have all heard about this in conversations with like other sort of senior team members, but like OEM's biggest problem is that we've never been able to thoroughly test a vehicle. And so I've thrown this slide up here, which is just kind of like a quick explanation of how I see the design cycle. So, and it really is a cycle, like it's always kind of a cyclic thing. Usually we start the year in this, oh wait, let me get my pointer. Yes, okay. We usually start the year in this upper right quadrant in like the design phase, right? And you guys have all seen that, you know, you've designed parts, you've looked at system requirements, and if you've been coming to the mechanical talks that me, Alex, and Neil have been giving, you know, we've talked about how important some of this stuff is like in the design process, and how important it is to have like useful requirements for your designs. So anyways, so normally we start here, and then we go on to analysis, and you know, we have these MATLAB models that we use to do some analysis. We have this software called Optimum Kinematics, which helps us do some suspension analysis. We have, you know, structural analysis of our parts. And like, we do a decent job based on the information that we have and the assumptions we can make, but again, still far from perfect. And then normally what comes next is you get to this testing situation. And what testing does is testing allows you to then take your system and evaluate it in real life circumstances. And when you do that, you will get an understanding of how well your system performs. And you'll be able to characterize its performance. And more often than not, it will not be performing as well as you'd like it to. So then you sort of take all this information from your testing and you use that to validate some of your design and some of your analysis. So you say, oh, well, in our previous analysis, we were expecting this much force going into the knuckle, but from testing, we learned that it was actually this much force. So now moving forward, we're going to update our analysis. We're going to update our design. So that kind of closes the loop and we get back to design. The problem with OEM is that we've almost never effectively been able to do the left half of the cycle. And this is something that I've seen for the last 3 years. It's something that all the other senior members of the team will tell you about. It's like a huge lack in our design cycle because we've never been able to categorize our system performance. We've designed 5 years worth of suspensions, but we don't know a dang thing about how well they do. Like we have no clue if they're good or bad. So that makes it near impossible to make useful decisions in future years. So the best thing that we can do as a team, fundamentally, at this point where we are at right now, I'm talking about. Okay, so what does this mean for like us as a team moving forward? Specifically you all, because I will be here, obviously. We get to test the car. You know, we have a lot of the work done for Mark V, and we're pretty confident that we'll get it running in the fall semester. And then we'll have almost the entire fall semester to be testing Mark V. And like, I know it's maybe difficult just to like see the importance of this because like, I don't know, like it's easy for me to see because I've like seen the failures of not having this testing information, but like being able to do this testing is like so phenomenally useful to our team. It is mind-boggling to me. Like, and I'm so extremely excited that this is the case. However, testing is a complicated thing. Testing is a very complicated thing. And I'm going to talk a little bit about testing for the rest of this presentation. But the sort of key takeaway here is that before we can even begin to design Mark VI, we need to be able to characterize the Mark V system, and we need to understand the suspension and handling so that we can make direct improvements to the design. So I know it's like I definitely hear all of the desire to like start learning about how to actually design the suspension and like start moving along in that design process. But I just kind of wanted to contextualize why we're not getting into that right now, because the testing of the vehicle is like critically important. And you can learn about like learn to characterize the system independently of like seeing the nuances and how you like set up the geometry of your A-arms. And that's like kind of a nuance point, but it's really important to understand. And so anyways, I'll pause there. I don't know. Any people have any thoughts, like any questions about stuff? Yeah, so sort of like, so fundamentally, that's sort of why I've been trying to like take a little bit of a step back. I'll get to that in a second, sorry. Okay, so, you know, I've been talking about testing, you're gonna hear about testing a lot, and there's gonna be another like full team mechanical presentation about testing, but I'm just gonna give you like a little snippet to contextualize the rest of this presentation. Okay, so what even is testing? We can test a design for many reasons. Like I said before, we can use it to validate a design. So say we have, like, we've done a lot of work on this like knuckle, and we want to make sure it's not going to fail. We can test to make sure it's a good design, that it's going to perform as necessary, and that it's good to put on the car. That is like a very basic test. Like, I have this part, I want to know if it's good enough, so I'm going to test it. If it passes the test, great, it goes on the car. If it fails, too bad, we'll have to redesign it. We can test to sort of fine tune a setup. So maybe instead of categorizing whether or not this part of the system is going to fail, we're trying to test to find how far from optimal it is and see if we can change parameters until we get it to a more optimal setup. We can use testing to validate or improve models. This is extremely useful because we use these models to analyze our parts, and we use these models to help us design our parts and our systems. So if we're making like critically flawed assumptions when we're making those models, that will really negatively impact our designs. And testing will sort of reveal some of those flawed assumptions. An example is like, you know, we assume that there's like a maximum load case on our knuckle, that's equal to the total amount of force that our tires can produce. And we sort of fudged this number because there's this little blurb in our testing, in our tire data that says FSA teams normally don't see things higher than 2/3 the listed amount of force on our tires. So like that right there. So like, we start with this number, like 1,000 pounds or something. And this little like paragraph is now saying, oh, you shouldn't design for things that are higher than like 700 pounds. That's like a pretty big difference that we want to know. Like when we're setting up our analysis cases, we want to know how much load we can expect. And right now we're just using unvalidated numbers from like a random paragraph and like graphs that we have not like seen the test for. We do not know how good they are, how accurate they are. But if we do our own testing, we can actually begin to find some of those numbers out and begin to like actually make useful models and useful analysis. And the last one is kind of related to the first one. Like we can just see how close to failing a part is. Okay. We can also test at many different levels of the car. And this is kind of an important piece to understand just from testing in all fields of engineering. Like there are all sorts of different scales that you can test things at. The most basic is a component level test. This is not even the most basic. A pretty basic one is a component level test. And this is where you take like a single part on your system and you set it up in some way that you can like simulate the loads it might see. And you're testing just how that part responds. So an example is like, I mean, we don't do this, but an example is like if we wanted to sort of like screw the knuckle into some plates and like pull on those plates in some direction. Like that would tell us how our knuckle responds to that force. The next step up might be like a subsystem level testing. So say like we wanted to assemble the entire ARB assembly and then mount that to something and then begin like cranking the bars. That would then be telling us information about how the sort of whole system responds, not looking at just how like a single piece responds. And then finally, we have like vehicle level testing. So this is where we've got the whole vehicle running. We've got all the different subsystems coming together and we're testing them all at once and trying to see something about how maybe our individual system responds. And the thing to note is that the vehicle testing is far more complicated, far more complex, and far harder to understand how specific variables will change what exactly is happening. So I'll get to that in a second. Okay, an ideal test is one where we are isolating a single variable. So in an ideal test, we have all of our assumptions covered, and we are testing one single thing, like one single part of our design. And this is because we don't want to be seeing like a result that's not caused. I phrased that poorly. I mean, it's basically what this point here says. We want to be confident that our results aren't being caused by something other than what we're trying to test. We want to make sure we have a direct understanding of how the variable we're testing changes our system. And if there's a bunch of other variables that are also changing our system that we're not realizing, then we have no clue if the variable we're testing is actually what's causing the change we're seeing. And so like a very classic example of this, I don't know if you guys have seen like the Instron machines in the MatSci lab, but like these are like some of the most fundamental testing tools that are used, because what this does in most cases is you take this little strip of material, like a little strip of aluminum, and you just yank on it at both ends and you see how strong it is. Like it is a very fundamental test. It is testing like one specific variable, and it tells you a lot of useful information because that's like a baseline assumption that you're then going to carry on through the rest of your testing and analysis. And so like companies will just like, a lot of companies you'll work at, you'll see they just have catalogs of, they call them like coupon tests because the little strips of metal look like little coupons, but they'll just yank these things until they break, record how much stress it had when it broke, and they'll use that as like a material model. So like, this is like a very sort of like baseline test. Okay. This picture here is an example of maybe a component level test that we ran. So a component level test is used to answer a specific question about a part. So the question that we had when we were, testing this anti-roll bar is, will the vertical forces that we're seeing from the suspension members bend the anti-roll bar so much that it breaks? And it just so happened that those forces were roughly equivalent to how much Yvonne weighs. And so we asked her to hang from it. But it does answer like a very direct question we have about our part. Like we want to know, will it break when we have these loads at the end? And so we applied those loads and it didn't break. And so we did have some assumptions in this, you know, like maybe me and Kyle weren't the most fixed supports and maybe Yvonne wasn't holding it at exactly the right points, but it's a pretty straightforward test, right? Like 2 fixed ends, 1 load, pretty straightforward, pretty reduced complexity. On the flip side of things, we have vehicle level testing. Vehicle level testing is extremely complex. We are testing dozens of parts, dozens of subsystems, dozens of interactions, and it's very, 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 very difficult to have an understanding of like how a specific change will have an impact on the overall vehicle, because for all you know, you're changing 5 variables at once. And it gets even more complicated when looking at something like a road vehicle, because now you're operating within an uncontrolled testing environment. Like the temperature of the ambient air will change our car's performance. The road conditions, if it's gravelly, if there's dead leaves, if it's wet, if it's windy that day, these all change our car's performance. And so it makes it kind of much more muddled, much more difficult to understand how a specific variable is changing the results we're seeing. And so you can kind of see like there's a spectrum here. If we look at this top spectrum, this is sort of like looking at the complexity. The least complex is a component level test, most complex vehicle level test. And so then to gain useful insight from these tests, you can look at this bottom one. You have to have an increased understanding of the vehicle system to gain any insight from vehicle level testing. When you're doing a component level test, like you don't need to know what the ARB does or how it functions or anything to tell me that like, oh, I put a load on it and it broke, right? Like that's a very simple question. It requires no understanding of the vehicle and you can give answers really quickly and easily. For the vehicle level test, if I ask you like, oh, how do you think our anti-roll bar is changing like our understeer in a corner? That's a much more complicated question. And that requires a much deeper understanding of the vehicle. So coming back to the sort of design cycle here, in order for us to actually have like a useful progress forward in the design, we need to be able to test the vehicle well. But testing the vehicle well is very complicated. And so this kind of brings us to what I'm calling the unfortunate life of a suspension/aero team member. And what I mean by this is that our job as suspension and aero team is to be the experts of understanding car behavior. And when I say car behavior, I mean like it is our job to have somewhat of an understanding about all the complex relationships that are happening in the vehicle. And to make our car go faster on the track, we specifically need to understand these complex relationships, because oftentimes when you're testing with a full vehicle, you're looking at like qualitative data, or you're looking at really complex or graphs that can have multiple meanings. And so you kind of have to have a qualitative understanding of like, how are all these factors playing into what we're seeing? Okay. So a sort of key takeaway here is that to understand, so if we understand system level relationships, this is saying like, if as a team, we can sort of have at least a mental model or a mental understanding of how different variables within the vehicle will change its performance, that will make us able to make sense of complex testing data. If we're able to make sense of complex testing data, then we can have an understanding of how Mark V performs. If we have an understanding for how Mark V performs, then we can make useful changes on Mark VI. Yeah, let's chat here for a little bit. I think I just said a lot. So how do people feel?
One quick note about the anti-roll bar testing. That's a really good example of kind of choosing or kind of choice of testing resolution and testing accuracy. Like, yeah, really low resolution, really, really low accuracy, but we were operating on an assumption that had literally not been tested or checked whatsoever. So it was better to have shitty testing data that was at least, you know, even if it's got like an ounce of truth to it, it's more helpful than nothing.
Yeah.
Should testing come before competition, and then after testing you like redesign and then make new part and then like use that for the actual car, or like how does that really work?
Yeah, your microphone's kind of weird. Sorry, but I did hear your question. I'm just gonna say it back to you. You can tell me if I heard it correctly. Coach was, should we test a car before competition and then go to competition and then make changes for the following year's design sort of after doing testing and competition. Is that kind of your question in a nutshell?
Yeah, or like should it be designed before the competition after we tested, or I guess yeah.
That's a great question. And I'll talk a little bit about that in a bit in this presentation. But there is to win a race. Okay, actually, I have a slide about this. I'm gonna skip forward a little bit. Oh Jesus. Okay, no. Okay. A race car is not a globally optimizable thing, which is to say that you can never make a perfect race car just like, and end there, because you can only ever optimize to whatever specific race you're like competing in. So you'll be facing different like situations and different requirements for every single track that you're on. So in order to have an effective race car, you have to be able to tune it to the track that you're racing on. And you have to be able to like have variables that you can change on the car itself in order to win. So it is absolutely essential to test your car before we go to competition, because all of our subsystems on the car, electrical, mechanical included, all have an amount of adjustability built into them. And we need to sort of find the optimal place to put all of those subsystems in to go as fast as we can. So for suspension, there's like specific characteristics in the suspension that we build in some amount of adjustability, and we plan to sort of like try and test the car in different circumstances to see which of those setups gets us around the track fastest. So there's sort of an amount of like design, test, and tune, and then go to competition, and then take all of your, but then ultimately, so once you've done like the tuning, ultimately there will be things that you cannot change on the car as you've designed it, that you'll have to make like a permanent change to the next year's car. Does that answer your question?
Yeah. Thanks.
If it didn't, like, please like ask.
Yeah. So I was just curious. So maybe like there would be two design or like two manufacturing cycles, I guess. Like the first time would be like all the initial parts, and then the second one would be like the ones after you tested it.
Gotcha. Yeah, that'd be a super like you would make a really good car if you did that. Absolutely. Like if you had the ability to make those like turnarounds between like having a testing vehicle and then remake some of those components into the new vehicle, that would definitely be like a very effective way to have a better like lap time. That just gets sort of into the complexities of like what it takes to build a vehicle, just, in general, if you will. And so we definitely like, in our timeline, we just have never been able to get the car done soon enough to make that a reality. But if we wanted to only compete every 2 years, that'd be like an awesome way to do really freaking good every other year. So yeah, that would definitely be a good strategy.
Race teams work. Like every Formula 1 team on the planet and every rally car race, they like make new parts between every single race. Like they experiment with different aero packages. And like we do the same thing, just on a much longer time scale due to our resources.
Yeah, like F1 cars have different aero packages for every race because they're tuning their car to the specific track that they're racing on. Because all the tracks have like far different like layouts, like different turns they have to hit, different speeds they're going at, very different weather conditions. Some tracks are really hot, really dry. Some tracks are wet, like more often than not. So yeah, they're changing these things like between races because they have so much money and so many engineers. It's insane.
Yeah.
What
they
sort
don't
of
have the money.
They also change races.
Oh wow. No, I was just gonna say, what sort of changes do they make? Like, is it like they have a couple different models? Like, oh, this model is good for like straight tracks. This one is good for circuits, and this one is good for like other types of tracks. Or is it like more precise than that? And like they have like slight changes in like, let's say like, I don't know, aero curvatures for like every single track.
Both. Some quick examples. Most teams have a different steering rack for Monaco than every other track because Monaco has such tight turns and low speeds, so you need tons of steering movement. They replace front wings and rear wings. There are also, the elements are slightly adjustable, so if you turn a screw, they'll rotate slightly. Also, during the race, the steering wheel has at least 4 different knobs, which manage engine performance, fuel usage, all those sorts of things, so that like if you're behind but your tires are fresh, you can turn up the engine to go faster, but you'll wear down your tires faster. Or if you're in the lead, but you're like gonna run out of gas before the race ends, or like everyone's way behind you, you turn down the engine a little bit so that you make it to the end of the race. They also have different tires for different weather conditions. They have wets and dries. They also have like 4 different compounds of dry tires, from like super softs all the way like ultra soft, super soft, soft, and medium, and hard, I think. And then they also have like wets and hards for wet weather. So there's like a million different things that they change, and all different combinations of it.
Are all the steering wheel controls like controlled by the driver, or are they like remotely controlled by the team?
No, that's one thing that the FIA has been cracking down on. There's only one person allowed to talk to the driver there's only one person allowed to talk to the driver the whole race. The driver has to make the adjustments themselves.
Okay. Cool.
They're trying to make it so that it's not robots driving the car, that it's still like actual like human racing.
Yeah.
While also including technological advances in race cars.
Makes sense.
Yeah. But if you like watch the Formula One like Drive to Survive show, they have a lot of that telemetry between the driver and the race engineer, and you'll hear them say things like, "Yeah, like turn down the engine," or like try to get some heat out of the rears. Like they're like constantly, yeah, I mean like they're treating the vehicle as a race, which is kind of sick.
Yeah. I'd say
the amount of adjustability that like a race team has is almost purely dependent on how much money they have and like what level they're competing at. Like Formula 4 to Formula 2 cars will have like Formula 4 cars will have different suspension setups where they'll have like different A-arm layouts and different like holes drilled in the monocoque, and they'll just like bolt on different suspensions for different tracks. That's kind of cool. So for us, like we don't have the money and manufacturing capability to do that. So we build in adjustability in like the camber adjustment, which is just a little shim we can add. The toe adjustment of the wheels, which is like just turning the toe rods, and basically just our ride height after that. So there's, we have more limited options, but they still exist and they're still important. Okay. Yeah. Anything else about sort of the goals of testing and why we might care? Cool. I'll do that. Okay. So I know I've been saying like how complicated the car is, which is true. I mean, it's extremely complicated, but I just want to highlight how much you can get and how far you can get in testing if you have at least a little bit of qualitative understanding between like important variables. And so a quick recap of what we've learned. We've learned about tires and the sort of their complex behavior, right? Tires can produce lateral force and longitudinal force related to the relative like slip ratio and slip angles. And the amount of force that they can produce is kind of fixed to the outside of that frictional ellipse. And the tires produce forces along that frictional ellipse, sort of distributed between lateral and longitudinal. And we know that the amount of sort of like the wideness of that frictional ellipse is critically related to how much normal force is on the tires. And we also know tangentially it's kind of related to how hot the tires can be. It also is related to the camber angle of the tires, which we didn't talk about, but it's kind of like, you can have like sort of an intuitive relationship, at least understanding that, okay, how hard I push in on the tires changes how much force they can produce. Like just having that understanding gets you a long way. And then we also talk about oversteer and understeer. And sort of in general, oversteer and understeer is a measurement of how much you're either like turning wider than the intended radius of your steering wheel is dictating you, or how much more you're turning, how much tighter you're turning compared to sort of like the geometric path of your turn might be. And we sort of learned a little bit about how that's specifically related to the yaw balance of your car. So how much your front tires and your rear tires are trying to rotate your car about itself. And we learned that sort of that is related to the center of mass placement of the car, how the different cornering stiffnesses of our tires, and then sort of like more generally how much lateral force the tires are producing. So we learned, I mean, it's a lot of stuff, and it's like a lot of important relationships. And even though it might seem like a lot, it might not seem like a lot. I'm going to kind of show just like just a little contrived example of what we might learn when we're testing the car, even if there's like little bits of information. Okay, so here's a little like I said, a little contrived scenario. So say we're testing our car and we're going around the test track, and on the corner number 4, our driver comes back and says, "Oh, like the car is understeering. You know, like I have to slow way down to take this corner." But you know, as the engineers, we're looking, and every other car appears to be taking the corner no problem. Like all the other cars that we're racing against are taking that corner at like 30 miles an hour, and our driver's saying if they try to take it 30 miles an hour, the car's understeering and they cannot make the turn. So now as engineers, we're like, okay, what's going wrong? What can we do? And so here's what we might say if we had no understanding of the vehicle system. We're sad. We're like, I don't know, maybe you're going too fast around the corner. Like, just slow down and be a better driver. That's like the easy, like sort of not intelligent response that one might give. Now here's us, big brain. Now that we know at least a little bit about vehicle dynamics, we're like, oh, understeer. Okay, I remember that is related to the relative cornering powers of the front and the rear. I wonder what might be impacting that in this corner. And we think a little bit more, and we're like, what was that weird presentation that Nate gave? Oh, well, the center of mass placement might have an impact. And we know that maybe weight transfer has an impact. And we know that the different cornering stiffnesses of our tires might have an impact. And we know that, like, you know, maybe the driver is just taking a bad line. That's something we should take into account. So we at least, you know, we have some relationships in our mind that we can think about. So maybe we can try and solve this problem together. Let's kind of go through the list of things that we sort of came to mind when we were thinking about understeer. So maybe we're thinking of like center of mass effects. Well, we've tested our center of mass and we know it's in the middle of our wheelbase, so it's probably not the cause. And for reference, this is something that we do. Like, we do try and measure our forward-rearward center of mass placement to get an understanding of, like, are we actually close to neutral steer from a center of mass perspective? Yeah, like we bought like 4 like Amazon like bathroom scales, and we literally put one under each tire and then find like the center of mass using that. Okay, let's maybe think about weight transfer effects. You don't have to worry about this line too much. I'm actually going to talk about this in a couple weeks, but let's say that we know that based on our different weight transfers and roll centers, this is probably not the cause of understeer. Well, okay, well now maybe let's think about lateral force generation. Like, we know this is like a pretty primary function of the tires, probably something we should think about. So what could be impacting lateral force generation? Do you guys want to just throw out some ideas?
Tire temperature.
Tire temperature, that's on here. I'll get to that one. I thought it was the first one I was wrong. All right, so they got temperature. What else might it be? I'll give you a hint. You just saw one.
Camber.
What else do we think?
Aero.
Aero, that's a great one. Yeah, that might impact it. Other things?
Towing,
that could definitely impact the lateral force, yeah. All right, so yeah, tire camber, but let's say that we accounted for the tire camber with our suspension geometry. Aerodynamic effects. That was a good question, Rohil. Maybe we haven't validated our aero. Maybe we don't know exactly what aero is doing. Uh-oh. Tire temperature. Uh-oh. We also don't know how hot our tires are. We don't know what's happening. So even just like with a little bit of thinking, we've gotten to some impacts that we have not tested and might be changing. It might be like impacting the understeer in that corner. All right, well, let's maybe dig a little bit deeper. So now we have at least 2 hypotheses now. We have hypothesis that maybe our aero is causing the problem and maybe our tire temperature is causing the problem. So let's look at tire temperatures first. So we have kind of a notion that maybe our tires are changing temperatures at different rates, or maybe our aero isn't putting enough force in the right place. So this is kind of like maybe something we've come to the conclusion of. So now let's try and look at the tire temperature one first. So imagine we run the track again. We're like, all right, driver, get back out, like drive. This time we're going to be paying attention directly to the tires. Fortunately, Kay was paying extremely close attention and noticed that on corner 2 and 3, our driver was pushing the wheels, was using too much force in the transmission, and our rear wheels were slipping well above a slip ratio of 2. So they're like dragging along the ground. And dragging the rubber against the road does heat the tires up. Okay, so now maybe we're learning something here. So we run the lap again, and this time we have the driver stop right before they get to corner 4, and we look at the tires. And sure enough, the rears are hotter than the fronts. So what do we think that's going to do? It's a hot tire. So do we think this would cause understeer?
You're going to get more lateral force generation on your rears.
Exactly. So we know if our tires are hot, they're stickier and can produce more lateral force. If our rears are hotter than the fronts, will that cause understeer? Yeah, because the rears are producing more lateral force, which means that we have less required slip angle at the rear to balance the car. And we know that our body slip angle is equal to our rear tire slip angle. And if our body slip angle is lower than it needs to be, then we're not going to take the path that we want to take around the corner, and we're going to understeer. So we're like, okay, you know, we're no vehicle dynamic experts out here, but we had some intuition about tire temperatures and how that might change our understeer characteristics, and maybe we've learned something. So we're like, okay, what can we do? So is this necessarily the answer? No, we know it's not necessarily the answer because the vehicle is far too complex and there's a lot that could be causing this. But we've learned something, and we have at least a hypothesis we can use to continue testing. Okay, so we say to the driver, okay, we're like, you know, you're trying too hard in corners 2 and 3. Take the lap again, but this time go slightly slower around corners 2 and 3. Don't like ease off the throttle a little bit, and then go take corner 4 at like 30 miles an hour. So the driver does this, and it still understeers. So are we just like complete losers? Are we nerds? Not necessarily. You know, we still have another hypothesis. We're thinking maybe the Aero package has something to do with this. And it's really important when we're doing testing to have an understanding of like the sensitivity of variables and how much changing one variable might have an impact on the system. And so I looked to see if I could find graphs of how much our tires changed lateral force with their temperature. We don't have that data, which is kind of a bummer. But I did some digging, and it definitely changes lateral force, but let's assume that it only changes like plus or minus 5%. Even though that does change our over and understeer characteristics, like maybe now we have an understanding that, oh, that's actually not the biggest deal in the system, and so that's not something we should necessarily be worrying about as much. Now, I went into this presentation, I wrote this all out assuming I'd get this data. I was pretty bummed that I didn't have it, but I'm just gonna acknowledge that here and we'll move on. Okay, so anyways, now let's look at the Aero package. Okay, so we're like the tire temperature's not the problem, but maybe the Aero package is. This slide kind of gave it all away, but so let's say we look at the downforce being produced versus the airspeed, so how much downforce being produced compared to how fast our car is traveling for the front wing and the rear wing. And let's assume that the this orange one here is the rear wing and this blue one here is the front wing. Okay, so say we're taking this turn at 30 miles an hour. We see that our rear wing is producing more downforce than our front wing. So what do you think that would mean without reading the point below, which lays it out?
Is that understeer once again because the rear tires can produce more force, lateral force?
Exactly. So with more downforce on the rear tires, our rear tires are generating more lateral force than our fronts. So again, we need less body slip angle, or less rear slip angle, therefore less body slip angle, therefore we're understeering again. So there you go. Now we've sort of learned a little bit about our system. And we can now say, like, you know, moving forward with our design cycle, oh, okay, like we really need to have an understanding of the speeds we're going to be taking our corners at. Like say, like maybe we picked these wings because they had like really great downforce at higher speeds, and then we're like, oh wait, we're never going to be at those higher speeds, and these lower speeds, it really causes like extreme understeer in our car. That's a really big learning point. Like if we're understeering that corner 4 every time, like we're always going to be slower. So even like with just a little bit of understanding about the ways that like lateral force can change and the ways that changes our over and understeer has a really big impact on our understanding of our vehicle. I know this is kind of like what I was saying before, there's no such thing as a globally optimized race car. So we're always thinking about how the conditions we're racing in change our vehicle and what changes we can make to our vehicle to best race in the conditions we're given. Cool. Any questions here? Oh, heat take.
Yeah.
Okay. Yeah, go.
I have a question. We said when it came to center of mass, if you have more mass at the rear of the vehicle, you get oversteer, right?
Yep.
Okay. But how come with like that other scenario we just went through, if you have more normal force on the back of the car, that's understeer? Like
so
aero package.
that's a really important question. I think we talked about this a little bit in the last talk. So the amount of lateral force, so sort of like the friction curve of tires, because you gain lateral force at a decreasing rate compared to normal force, you can consider that like a less than linear relationship. Whereas the amount of slip angle required to balance the car is a directly linear relationship because it's just like a force moment balance. And so the linear relationship has a stronger impact than like a less than linear relationship between tire load and lateral force. And so it ends up being more important where your center of mass is from a yaw balance perspective than it does from a lateral force generation perspective.
Okay.
Does that make sense? I can draw it out. I can annotate this. So like, here's lat force. Actually, this is, okay. Do you remember what the, what's it called? This is going to be lateral force divided by normal force. Is this what I want? I think it's what I want. And this is going to be this relationship sort of looks something like this. As in like, you don't get a linear gain in lateral force with like a gain in normal force. Like normal things look like this. Tires sort of look like that.
Okay.
And so what that's saying is like, as you are increasing your normal force, you're not gaining lateral force at a proportional rate. But when it comes to slip angle generation, so here's like, what am I draw here? This is, this graph is gonna be useful. No, let me think about the best way to draw this.
The kind of, the reason is that like your center of mass, the location of your center of mass relative to your forces front and rear, it's kind of like a lever, like a seesaw, where it changes the kind of effect that the front and rear have on rotating the car. So if you change the position of center of mass, so like the rear slip angle is dependent on the front slip angle, which is dependent on your steering input. But the rear slip angle is also dependent on the location of your center of mass, because it's a moment balance. Because the rear slip angle, or the rear lateral force, has to balance the torque generated by the front slip angle if you're in a static case. Because like, you know, static cars like moving through the turn, but it's not actively rotating. You've already initiated the rotation and you're just carrying that through the turn. And so the moments have to be balanced, and the moments are all summed around your center of mass. So if it's really close to the rear, you need a higher rear force to balance your front force. If it's towards the front, you need a higher front force to balance the rear force. So this
relationship here is like what we call linear, right? Because there's no exponentials in here. It's like, as I was saying, like as you move your center of mass, as you change A and B, the force, like required force changes are like directly linearly proportional to that. Whereas the lateral force versus normal force is like non-linear and like decreasing. Okay. So this relationship wins out over this relationship.
Okay. So, and the normal force isn't affecting like the moments at all, right? Okay. I think that makes sense.
It's complicated because it's like the lateral force generation at the front and rear they're both functions of multiple variables. So lateral force at the rear is a function of the location of the center of mass, but it's also a function of normal force. And normal force is also a function of center of mass. So if you move the center of mass, you change the kind of moment balance, but you change the normal force. However, if you get a case where you can decouple the location of the center mass and the normal force on the tires
as you can with an Aero package, you can either make things worse or you can make things better. So that's kind of the key point here, is that without moving the center of mass, you can affect the system by adding more normal force.
But it doesn't affect the system in the same way.
Yeah.
Okay. Cool.
Because in one case, you're changing two variables at once. In the other case, you're only changing one of those variables.
Yeah, exactly.
Okay. Awesome.
Cool. So, yeah, like, and that example sort of covers like how complicated the relationships can be, and like there's a lot of coupling between a lot of the factors and variables that we change. And so having an understanding, that's kind of like the sensitivity point that I was trying to make before with like the tire temperature. Like, say tire temperature is even less important than normal force, right? Like, we know the normal force has some impact on the amount of lateral force we can generate. And say tire temperature also does, but say tire temperature only affects it like 1/10 of the amount, right? Like, we would care a lot less about tire temperature. Like, we would want to look at that later in the system than looking at like the more impactful things. So, but that being said, even though the relationships are complicated, like the things we've learned in the last couple of presentations are like some of the key relationships. And if we can think about ways that other variables are changing things like lateral force and things like normal force on the tires, that will always give us some insight into whether or not we're like adding over or understeer to our system. So the last thing I want to sort of wrap up with here is actually what sort of tools we have when we're testing the car. And this like topic requires far more than like the next 4 slides I'm going to give, but I think it's cool to sort of start to put some intuition into your heads of like, what on the actual car can we do and how can we learn about our system? So the first thing that we have that is like, and this is all, you can also talk to Lucky about all this stuff because he sort of heads up, or he's currently the head of like the sensing electrical sub team. And we've been working with them to sort of like figure out what the best sensors we can use to learn about the suspension system are. So the first one are things that we call strain gauges. And what a strain gauge does is it looks at how much your part is like deforming. And if you know how much your part is deforming, you can figure out how much force is going into it to cause it to deform. And so ultimately what the suspension strain gauges are telling us is how much force is going through each suspension member. And if we know the force going through all of our suspension members, we can use sort of like an equation that we have to calculate how much force our tires are producing. And you can imagine how extremely useful this would be if we're trying to see whether or not we're over or understeering a corner and due to what effects, because we can directly see how much more force like our front or rear tires might be producing, or how much more force our outer tires might be producing compared to our inner tires. That's an extremely useful tool for us as like a suspension team to sort of understand our system a little bit. The next sort of sensing tool that we have is called a linear potentiometer. And what that does is it just gives us like a linear measurement. And so we attach this to our suspension springs, and our suspension springs are going to compress and extend, meaning they're going to change in length. And so if we attach this linear potentiometer to both ends, it will tell us how much our springs are extending or how much they're compressing. And this gives us a lot of information about the weight transfer in our car. And so say like we're taking a corner and we see that our outer springs are compressed like a ton and our inner springs are extended a ton. Well, now we know that there's a ton of weight transfer occurring, and maybe that's more than we designed for or more than we expected. So now we have an understanding of why our car is not cornering as well as we expected. It also tells us how much downforce we're getting, because if we look at how much our springs are compressing as a function of our speed, we can get an understanding of how much more force is being added on the car that's causing our springs to compress. And that's also a really important metric to understand, because as our springs are compressing, that means our suspension system is actually moving in 3D space, because our suspension and our springs are like directly coupled. And so say we're taking a corner and our Aero package is squeezing us into the ground a lot, but it's actually, we did a poor job designing the suspension, and we were expecting to take the corner with our springs compressed this much, which caused our tires to go upright. But now with our Aero package, our springs are compressed this much, and that's caused our wheels to move up, and our wheels are cambered in 10 degrees. Well, now we're going to not take that corner very well. And so that's like a really important aspect for us to try and understand how much the Aero is impacting our like suspension characteristics. We also have an accelerometer and a gyroscope on the car. And this measures our acceleration in the X, Y, and Z axes, as well as angular velocity of our car about those different axes. So that can tell us things like how much our car is yawing. I don't know if you guys remember, there's sort of that like damping term, which is related to as our car begins to turn, how much our wheels are trying to like fight back our car turning. And that's related to how quickly our car is like yawing about its center axis, like how quickly our car is pivoting. And so understanding that will help us understand a lot how much our car is responding and being damped in a transient corner. Sorry, that was probably a little bit too much. And also more importantly, it can help us make a GG diagram of our car, which if you remember from like the first talk I gave to the whole team, the GG diagram is a really great way to characterize how well our driver is doing. Like say we put one driver in the car and they drive around and they've got like a big old GG diagram, and then put another driver in the car and they're like only barely getting to the car's peak accelerations. Well, now we have useful data to tell the drivers, like, hey, it looks like you're really like willing to corner hard, but we noticed that your rearward accelerations were like really terrible. So you should like be using those brakes more. We also have tire temperature sensors, and a tire temperature, as we know, can change the amount of blood force, but also tire temperature patterns can reveal uneven heating of the tires. And if our tires are being heated unevenly, that can imply that we have incorrect camber settings, meaning our tires are tilted too much, and as we're turning, the insides or outsides are getting too hot compared to the rest of it. It might imply we're having incorrect tire pressures. It might imply some other things about our suspension geometry. And so this is also a really useful tool for us to visualize sort of like what's happening to our tires. And that will tell us like what our suspension is doing. So yeah, that's it. Any questions about those sort of like different sensing mechanisms?
Just because the incorrect tire pressures, how does the temperature, like of that affect, like how does pressure affect temperature?
Yeah, sure. So your tire is kind of like a balloon, and like as it inflates, it can kind of change its shape, and it'll also change where it's applying force on the ground. And so if your tire is underinflated, what's going to happen is the actual like, it's called the sidewalls. I'm going to point with the pointer, but you see like the leftmost and the rightmost sides of the tires. Those actually have like steel cables in them. And you can see there's sort of like more rubber in here because there's this whole sidewall section as compared to the middle where it's just like a thin bit of rubber. And so when your tires are underinflated, the sidewalls of your tire actually take more of the force than the middles. And so what you'll see if your tires are underinflated is the outer rims will be getting much hotter than the inner section of your tire because those outer sections are taking all the weight.
There's also a good relationship between tire pressure and tire wear. So like even if you like look online of like how to tell if my tires are like worn like on a passenger car, they'll give you little diagrams of like if the outsides are really worn but the inside is fine, your tires are underinflated. Or if the inside is really worn but the outside edges are fine, that means your tires are overinflated because it's ballooning up. Or like if the inside is worn but not the outside, that means your tire is like cambered wrong. And so there's ways to like check your alignment, and that's also related to heat because friction and heat are proportional. So if you're getting more wear, you're going to have more heat.
Cool. So as I said in the message, I think we're going to switch from RCVD to a book called Tune to Win. I sort of like default to RCVD because it was where I learned sort of like a lot of this stuff, but as like some of you sort of point out in the feedback, and definitely like I've noticed this too, like it's very dense. It's kind of hard to read and hard to slog through. And as I was just kind of talking about this presentation, I think it's more important that we, actually I'm gonna stop sharing. All right, sorry, can we stop recording from this point, Kyle?